Season 2, Episode 2, Take 1. Welcome to Quantum Kinetics First Diffusion, Season 2, Episode 2. I'm here with...
Jason MacCoy.
Jason, it's so good to have you back, as always. So what are we going to be talking about today?
Well, last time we talked about the tuning forks and the resonant chambers, and I got a second resonant chamber tuning fork thing.
Perfect.
One of these, and now we have two of them.
Here, let me grab one of those.
So they're twice as cool.
Okay, so I've got the A.
Right, and I've got the B. They're the same. They're supposed to both be tuned to 432.
Okay.
But I was wondering if something broke in the universe or in physics, because I was hitting one and the other one wasn't really ringing.
So just for the audience, just in case you missed the first episodes, is the phenomenon of the quantum tunneling or the quantum entanglement, is that like radio waves, is that if Jason were to ring the 432B and the resonant box could pick up that signal like a radio signal, and then this one would start ringing too. But it didn't work. It
did not work. And I was wondering, I thought I have a 432, the other one's a 432, they're by the same manufacturer. The number on the thing says 432. So what's going on? Why do you think it didn't work? What happened?
So we had to dive a little bit deeper into why it didn't work scientifically. And what we did was we got an audio signal generator that detects the audio signals from the tuning fork. And we found that I think it was A was 445. And then B was 430 or 440 or something like that. It wasn't quite right. And that's the thing about radios. And that's also the thing about, Quantum Kinetic Well technology, is that you have to be exactly resonant with the frequencies of sound between the two mediums. And if you're just a couple notches off with the frequency modulation, the amplification won't work.
It doesn't resonate, right?
It resonates just a little bit, but it's just like if you were to tune, your radio broadcast signal. You're like, okay, 106.1. But if you go like 106.0, you can kind of hear the station, right? It's like kind of there. It's all kind of staticky.
Yeah.
But if you click it back to 106.1, bam, you get a good strong signal.
Yeah.
And that's the same thing that happens with our tuning fork experiment. It didn't quite work, but doesn't mean it's not gonna work. Just didn't need to figure out why it didn't work.
Well, I guess the answer is they're not vibrating at the same frequencies, right?
Correct. It's like if you have a really cute girl walk in the room and there's tons of cute girls in the room, like say at a fraternity or whatever you have at a party. There's tons of really cute girls, right? But there's that one, right? You're like, oh my gosh. You see her and you go, oh my goodness, like I gotta go talk to her. There's something about her. It's the same phenomenon. It's an attraction.
Huh. Well, that explains why the tuning forks were a little bit off there. They were different frequencies, therefore they weren't resonating at the same. Hitting one didn't amplify the other because they're not exactly the same. Therefore, you don't hear the other one resonating with when you hit A, B doesn't resonate. So.
Correct. They have to be totally matched for them to reach the highest vibrational amplitude that's possible in that system or that input to the output. And if you don't hit it just right, it just won't do anything.
Yeah, that same idea is found in music. So if you like, I'll play a C major scale.
Sure.
But the last note I'll play wrong.
Go for it.
Okay, and you'll hear it.
Oh,
right?
Yeah, it just kind of like stings
it's
a little
off,
bit.
Right? I went one over, right? Okay, but this time I'm going to go one under.
It's still not quite there.
Okay, now this time I'll go octave to octave.
And then it just falls right into place.
Yeah, and here's playing the octave. So all of those are the same note, They all resonate with each other, right?
And it just sounds so smooth. It sounds so right. It just sounds like, it's like if you went and talked to a beautiful girl at the party and she was like, hey, I like you too. It's like so easy, right? It just flows right into the next thing.
When things are going well, yeah.
Yeah, but when they're going bad, they're going real bad.
That's when you get dissonance.
Yeah, absolutely. So now I think you want to talk a little bit about, let's go ahead and open our Red Bull. Now that the nerves are gone. So cheers to you, buddy. Thanks again for coming on. This episode is sponsored by Red Bull. Just kidding. So you want to talk a little bit about the periodic table and the electromagnetic spectrum?
Yeah, when my son was growing up, I had the opportunity to be a part-time stay-at-home dad. I was teaching at the UW at night, which is probably where you
and I we met.
Connected. Yeah. So when he was like 7, I was thinking to myself, well, the other part of it, it came from, he went to a Montessori school, and they have this concept of taking a child and teaching them about like their family and then their community, and then they sort of go out from there. Mm-hmm. And I got to thinking like, well, if I'm going to be able to spend time with them and teach them about the world, what is it that I'm going to teach them about? And I kind of came to the periodic table, because periodic table is matter. Mm-hmm. And the electromagnetic spectrum, because that's energy.
Photons, yeah.
Yeah, and I was like, those two ideas seem to go really well together.
Well, that's the premise of Einstein's equation, E equals mc squared, is that matter and light are basically the same thing, just in a different form. Huh. And matter is a potential release of light. And when you hit the stones together, you see sparks and you see light and stuff happening, right? And like when you dead short a battery, you see sparks. It's just matter, electrons turning into light, and that's what you see. And that's really the entire universe, is E equals mc squared. However, the equation is not quite right. It's E equals plus or minus mass times the square of light, which we talked about before on this podcast. Is that there's a duality between, when you have an electron, you also have to have the conjugate, which is the opposite charge, which is a positron, which is a positively charged electron. And when they touch, what do?
They destroy each other, right?
Well, typically they destroy each other, but in this situation, we're hearing what?
Them clinking together.
And that's a sound wave, which is also in hertz, which is photons. Okay, just so you know, a sound wave is exactly the same as a photon.
Really?
Yeah. I'm putting in energy, I'm getting energy out, but it's a different sound wave. Huh. It's actually in hertz.
I thought a sound wave. No.
Oh,
okay, here we go.
Good.
Oh, snap. Here we go. Okay.
Oh, this is good.
I thought a sound wave was a compression of air, and your ear drum hears it because it vibrates, and then, by the way, it gets amplified in your ear by
what is it? It starts with a C, right?
Well, the cochlea.
Yes.
But there's a 3-bone structure that amplifies. It's super interesting when you actually look at the ear. Like that, there's 3 bones that link together to amplify the sound. I mean, how crazy is that?
3-body gravitational problem.
Wow. So, but when you clank something together and it's sending off stuff, what is that? Isn't that just?
It's a perturbance. It's a wave. Okay, so there's 2 different types of waves. They say there's a compressional, which is longitudinal, which just means that it's going like this.
Is this like slinky stuff?
Yeah, it's a slinky going like that in a longitudinal fashion. And then the slinky can also go like a snake. It can do this, right?
On a different axis?
Yeah, it's on a different axis. This is I guess you would call that an x-axis.
Okay.
Right? And then this would be on a z-axis if you were in 3D Studio Max, which is kind of weird because it's not exactly Z, but so the point is that like you can have waves in different axes.
Okay.
But they're still waves.
Huh.
They have a frequency and they have an amplitude. A compressional wave also has an amplitude too. How pressed they get versus how much they push back.
And this has come up a lot on the news because we've had a lot of earthquakes and a lot of volcanoes. Mm-hmm. And they say that the Ring of Fire, just getting off topic a little bit, but
earthquakes,
yeah,
waves, no, it's all good.
And they say there's a big difference between a magnitude 8 and an 8.8. Like there's one in Kamchatka that was an 8.8. That's a big earthquake, right?
It's a bad
Why
one.
does that number? Why is it so much more going from 8 to 8.8?
I think I don't know because I'm not a geologist type
Yeah.
of person, but it's kind of like it's like a pH.
They call it the Richter scale, right?
Yeah, the Richter scale
Yeah.
of 8.8 or 8 or 7
Yeah.
or 4. It's exponential. It's just like pH levels in water, right? Like you can have a 7, but if you go to 8, it's actually an exponential growth factor of like how much oxygen's in there. If it goes up to 8, if it goes up to 9, it goes up to 10. Those are exponential values for the concentration of either oxygen or hydrogen ions or whatever. But so the earthquake sound waves, if I hit it really hard, yeah, it's the compressional acoustic, but it's still, even though it's longitudinal, it's still technically electromagnetic radiation because it's in hertz. The units do not change, right?
Yeah.
So
the frequency changes, not the
right. And that's the thing. It's all about different types of mediums, and this is why our technology works in water so well. Is that water is funky. It's really funky because sound waves travel really fast in water.
Right, yeah.
And that's one of our, the things that make our technology work, like we like to talk today about the Quantum Kinetic Injector, which was granted patent access on July 4th, 2023, which is Independence Day. It's very interesting.
Huh.
But the Quantum Kinetic Injector is very similar to the tuning forks because you have the body, which is the base, and then you have this probe in the middle that sticks out, and in between the space of the probe and the body, when you put the housing on, it creates a tuning fork resonant chamber inside the tip.
That cylinder is a resonant chamber?
Yeah, the tip region that you can't see because I covered it up, but this actually acts exactly like if you were to hit this. This also will resonate too as the water and the water mist in the air goes through this. It's actually what goes inside here is water, ambient air, and ionized gases, plus exhaust gases that go into here. And as it comes out the tip, we hit it with a very resonant pulsing frequency that instantaneously explodes the water inside a cylinder or at the end of your repulsor technology. So the Quantum Kinetic Injector is just a macroscopic scale of the repulsor tech that we have patented and trademarked here at Quantum Kinetics. And, we're ready to go into actual production. We'd love to, but we need to get some, more people involved and get things rocking and rolling. But yeah, it's, we're just so excited here at Quantum Kinetics because we're using real physics. We're using real, technologies that actually do work. We've studied them, research verified them, and we're just so happy to teach you guys about the quantum world. And there's something that I kind of want to talk about a bit with you, Jason, is the Heisenberg uncertainty principle.
Right.
And what do you know about that?
Well, besides Breaking Bad, did you ever watch that show?
No, I'm too busy in the show to be watching TV.
So the main character is a science teacher, a chemistry teacher.
Is he growing like weird cocktails or something?
No, he's creating.
Oh God!
We digress.
Yes.
On that one. But that's okay. So let me just spell it now that we said
that. Got the elephant out of the way.
Yeah. So he's a science teacher. I mean, a chemistry teacher. He gets cancer, I believe.
Okay.
And he's only got a certain amount of time to live. So he's like, screw it. He's going
for it.
I got to make money to survive. And he hooks up with this guy who's doing that. Because of his background, he knows how to make the product even better. And when the gangsters ask him what his name is, because he's a chemistry teacher, he says his name's Heisenberg. And he's like, "You're goddamn right." Like but so anyways, if there's besides that connection, he says Heisenberg because of that. But what I understand about the Heisenberg uncertainty principle, this is the way I sort of think of it.
Sure.
It's like there's a particle in space, but it's not in one point in space. It's like in a three-dimensional sphere of presence.
Mm-hmm.
And there's certain probabilities that it's in the middle or on the outside or somewhere in that sphere.
Sure. Yeah.
And it can be in all of those places, and it can pop across barriers because nothing can stop it from popping across a barrier because it's somewhere in that sphere. Is that kind of how it works?
Yeah, you did a very good job of explaining it. Essentially, it's the equation for Heisenberg's uncertainty principle is if we have a particle that we want to measure, let's say it's an electron, we want to measure its location. If we try to take a device and measure where it's located in the sphere here, we can get a good approximation of where it's located. But when we try to measure the energy level at the same time, we have no idea where it is. It could be energy level could be any energy level. But if we measure the energy level and then we get that, we will never know where it's located. So the electron is this really weird, some would say superluminous, which means it's not really in this dimension, but it is in this dimension. It's kind of like all over the place, and we can't lock it down because it's so probabilistic. What was that toy you mentioned at lunch that when you let the balls fall down, it creates the probability they were falling?
It's like a pachinko game?
Pachinko. It makes when all the balls fall down.
Right. A distribution curve of some kind.
Correct, and that's what we see with the photon going through the double slit experiment. Is we see the probability of where it's going to be.
Right.
It's not like I'm taking a ball and I'm throwing it through a hole. It doesn't just go through and hit the back straight. It actually can veer off, and the more times I do it, you get that probability. And so the importance of the Heisenberg uncertainty principle with quantum kinetics is that the classical world is only so good at certain things, but the reality of the universe is that we're actually in a quantum state. And that's where our electronics here at Quantum Kinetics really dives into. And this is why most people are like, you can't do that. That's impossible. That's breaking the laws of Einsteinian physics, blah, 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 equals mc squared. Well, no, we deal with a different type of quantum, not classical quantum. And I also want to make a mention that, Einstein never received a Nobel Prize for general relativity or special relativity. Why? Because they're wrong. And the only Nobel Prize that Einstein ever received was for the photoelectric effect and the quantization of the photoelectric effect. The thing about it is Einstein didn't discover the photoelectric effect. It was Hertz, Hertz. He discovered it in an electronics tube when he was shooting electrons, and they were hitting a piece of metal, and it would cause a voltage and an amperage.
Now, I've heard a couple times you say something really interesting. E equals mc squared is actually is it plus or minus mc squared?
Mm-hmm.
Okay. Why does that distinction make a difference? Why plus or minus? What's plus or minus?
So the plus or minus represents the positive mass of an electron, because that's something that we can see and interact with. And then there's another particle that comes along with it, which is called a positron or antimatter. And they're kind of stuck, they're linked together in a quantum entanglement way. And they're kind of squishy. Like they can, if I move this one will move, try to keep up with it. It's kind of like it's magnetically locked almost, like a quantum locked particle. And so that's the equation is Einstein only equates for this, a ball rolling on the ground. But he doesn't equate in his mathematics for this, where this is actually just as important, this antimatter is just as important, if not more important, than the real matter.
So when most people think of antimatter, they think if you put matter and antimatter in the same place, they destroy each other. And
if they touch.
If they touch, and then they release pure energy, right?
It just, the matter, the mass, once that matter touches, like matter and antimatter, they touch, it's called an annihilation.
Right.
When they touch each other like this and they cross through each other, there's so much, it's like a portal opens and there's all this light comes out. And then that light that propagates away goes into the universe, causing light to scatter about in the vacuum of space, which some would say that the quantum vacuum flux, that jittering action, which we talked about in other episodes too with Brighton, is that quantum jittering action actually is causing the expansion of the universe, because when the matter and antimatter appear and then disappear and then they emit light, it's actually causing the universe to actually bubble out. Like an expansion.
Is it sort of pumping more energy into the universe?
From another dimension, yes.
And that's expanding it.
Yeah.
Huh.
Yeah, and there's a certain point where it takes hundreds and hundreds and hundreds and billions of years for this to happen, but it'll expand out and then it'll slow down and then it will come back.
Like big crunch.
And it will do that. It just takes tremendous amounts of time.
Yeah.
It's called a great time. Some call it that. It's a great time. But apparently there's 7 of them. But anyway, the point being is that E equals mc squared plus or minus is critical to understanding the universe itself. And Einstein even thought, when, back in the early 1900s, is like, he thought, one, the nuclear bomb is not possible, which was wrong. He thought that the universal constant expansion of the universe was silly and that wasn't a thing, which is wrong. Hubble expansion, we discovered that. He also, there's another thing, I'm trying to think, there's another thing that he thought was silly, but I'm trying to blow on a little bit of a blank on, there was another part that he didn't like, but it turned out to be right. It's quantum. It's the quantum, the quantum mistake. He thought that, God doesn't play dice. It can't be quantum probabilities. God doesn't play dice. Well, I'm sorry to say that, who are you to say that, the universe doesn't just do what she does randomly?
Well, I would think of it like the law of large numbers, right? Like enough rolls. When I teach computer science, one of the projects I have is called a dice roll simulator.
This is going to be good.
I know.
I already see it.
You roll. The idea is you make a program that rolls a 6-sided dice a certain amount of times. If you only roll 10 times, your deviation from the norm or from the average is quite a bit. But if you roll 1,000 times,
right,
and then 1,000,000 times, you're right down there at like 3.5, which is a 6-sided dice between 1 and 6. Half of it is 7, half of it is 3.5. That's the average. If you roll enough times, you almost always get right by that average. So is it possible we just live in a giant soup of math that on average and in aggregate like does have a structure to it?
Well, I would say that there's like, for example, if you look into space in a very small section, let's just say we look up into space.
Right.
And we look into the stars and we see galaxies. Like we get the Hubble.
Right.
We take this shot and we see this randomness in just this space.
Yeah.
And we take a picture of that, and then we move to another quadrant, and then we take a picture of that. And we keep doing this like we're rasterizing a rendered image of the universe. All of a sudden, Jason, this picture of what appeared at first to be random actually looks at the big scale to be organized chaos.
They call it the cosmic web, right?
Yeah. Like a neurological pathway.
Yeah, it even looks like that. It's or like inside of a sponge. It's amazing.
It really is, and I'm going to give you a secret, ladies and gentlemen, that when you do cold nuclear fusion, which you just saw in the lab just a few minutes ago, is that when you're doing cold nuclear fusion and you're doing it right, the universe starts creating this spongy material that looks like neurological pathways, like the universe is trying to expand and learn and be unison with the world. And the thing about it is, like, this quantum kinetic injector uses high voltage as a Z-pinch. This is a Z-pinch fusion.
By the way, can I pick up one of those things?
I just want to make sure it comes out. Yeah, there you go.
Okay, yeah, I didn't want
I think that's a good one.
Mess around with the gear with that.
So the thing about it is, when you use a Z-pinch fusion event at high voltages, it actually pops. It blows up, and it makes, depending, okay, and here's what we found, Jason. This is crazy. And we talked a little bit about this already, but if you put in tap water into this thing, and it pops the water, instantaneously explodes it with a Z-pinch fusion, you'll get, with tap water, you get a blue light.
Okay, let me ask you a real quick question. When you say it explodes, okay, so I'm thinking you got H2O.
Yeah.
And you said it explodes.
Literally instantly.
But like, I think most people are thinking, oh, when he says explodes, it means electrolysis happens, and then you have an oxygen and a hydrogen.
Correct.
2 hydrogen, right? Or
you get 2 hydrogen. Well, and yes, in this situation, we get 2 hydrogen and 1 oxygen. Yes.
Oh, yeah. Okay, yeah, there's 2 hydrogens.
He's numbered notes. He's good with numbers.
I've got so many numbers in my mind sometimes. It just like, I actually had a...
you almost diverged.
I had a hard time doing basic math the other day because I'm thinking about music theory so much that it's like, I was trying to add 9 and 2 together, and I'm like, aren't they 3 apart? I'm like, because there's the difference between 9 and 12 is 3 apart, but
sure.
You start thinking along those lines.
Well, you know what your brain's doing is it's thinking in patterns.
Yes, absolutely. But let me get back to that thing. Like, so what's happening? When you say you put in water and it explodes, are you doing? Does electrolysis happen real quick, and then you're combining hydrogen and oxygen to make a explosion like they do with the space shuttle?
Yeah, exactly. So this is basically an instantaneous water thruster explosion, kind of like Iron Man, how he flies. And remember, in Iron Man the movie, his repulsor technology that shoots out is a yellow flame. It's a yellow flame. Just remember that. So when you put in the water mist, like say it's tap water, it comes out instantaneously polarizes the water into a gas.
Okay, yeah.
And because there's so much voltage gradient, and which has a certain amount of joules energy in it, it automatically ignites it like a flame. Pow! And then the water explodes as a explosion, and then it recombines right back into water again.
So it does do electrolysis real quick. Then the oxygen and hydrogen recombine,
exploding. Well, actually explodes first, then recombines.
Right. Because it's the
matter antimatter agitation to cause a light to come into the universe.
But isn't oxygen and hydrogen coming together a chemical reaction?
Well, technically, yes. So what happens with the oxygen molecule? There's one of the valence shells of the oxygen, I think it's the L orbit, has the ability to absorb some electrons. And because hydrogen is just a proton and 1 electron, what happens is the oxygen grabs the 1 electron around the hydrogen and gloms it into the valence shell of the L orbit, thus creating the bonding action to make the water molecule.
So this suit, here we go.
His brain's opening up.
The suit.
Yes.
Are you going to have to pump water through it?
Yes.
Yes. So you're going to have like a backpack with some water in it, or can you get it from the air, or how are you going to fuel?
Well, that's proprietary, but yes, it is water. Very good question, and the answer is yes, and yes. There's many different ways to do it. You can have a water pack on here. You can even use urine. Did you know that?
I hadn't thought of that.
And actually, in the movies, Tony Stark and Robert Downey Jr. and he's at a party and he's kind of drunk and showing off his suit and stuff. And he's like, "Yeah, what do you have to do?" If someone asks him, "What do you do when you have to go pee in the suit?" He says, "Well, let me show you." And he just urinates in the suit because the suit it absorbs the water of the nitrogen laced water, which when you pee, it is water. It's just got a lot of nitrogen, and that's why it looks yellow. Yeah.
Wow.
And you could use urine. Yes, any type of liquid that is water based, you can do this. And the hot fusion guys, what they do is they're using Z-pinch. They're putting in deuterium.
What is Z-pinch, by the way? What does that mean? Z-pinch?
Okay, so if you look really close at this thing, I don't know. We'll do a B-roll, but you look really close. It has a tapered edge here, and there's the housing has a tapered edge deep down inside there. And as the water mist is coming through the nozzle, it literally will taper down to the very end point. And then as soon as it leaves the tip, it explodes and then recombines back into water. and then you can actually recirculate that back into the tank with a pump. And
so this is is this a spark plug that you've modified? You've added the resonator thing on it.
Yes.
Gotta explain your technology.
Yeah, and see, if you just look at that, the threads. This is a 14 thread, 14 mil thread that goes right into any type of traditional, internal combustion engine.
That's so cool. So this technology could be used in cars directly, right?
Yes, it could actually. Yeah, totally. It just takes some money to build the units and get things rolling, rock and rolling, but the technology it does work.
So that's a topic to kind of clarify a little bit. You talk about getting the whole idea of being able to take an idea commercially or, and really help the world with it. In a way, you already have working prototypes,
correct,
right? This isn't about getting funding to make a prototype,
right,
but you need the funding to take these prototypes and scale them up, right?
Yeah, and so if you go back to like Elon Musk when he first started Tesla, okay, the first thing they did was he put $6.5 million into this, company that was in Silicon Valley working on electric cars just for fun. He became the owner of it. They got a roadster going. They proved that it worked, and they were super excited. And then they were asking themselves, well, how do we get this into the market? How do we make a mass production of these things?
Right.
And that takes hundreds of millions of dollars, because then you got to get a warehouse. Yeah. You got to get the sheet metal bending. You got to get the giant gigapress. You got to get the batteries.
Yeah,
you got to go to China to get the materials. You got to go talk to Mexico to get the electronics. You got to go everywhere, and it becomes this huge ordeal of getting it to production state.
Yeah.
Which costs a lot of money. And the point is, everything starts at this prototype level, which we proved and patented. It's who can get behind it to make it come to realization.
Okay, so I imagine there's a lot of people out there, forgive my French here, but they're going to say it's bullshit. They're going to say you just MacGyvered something in the garage, and it looks cool, but does it really work?
Yeah.
And you would say to that you have studies and government.
Well, just to be clarified, the water-injected spark plug or the Quantum Kinetic Injector is not government studied. That's just a patent and a device that we've proven and we've shown, in B-roll here, that essentially you put water through it, which I didn't even get to talk about the different types of waters, because we went to a different mode of thinking. But what we found, this is what's so cool. I mean, my goodness, guys, we're on the frontier of something really amazing here, because what we discovered through lab experiments is that when you put tap water, which has, there's trace elements of calcium, there's trace elements of silicon, there's trace elements of magnesium.
There's stuff in the water.
Yeah, there's stuff in the water, but when it goes through the injector and explodes instantaneously with this nuclear fusion voltage, the explosion of tap water is blue and white light.
Yeah, I saw the picture. It's amazing. Yeah, it's cool.
And when you put seawater through this thing, the color changes to a bright yellow orange flame. And I find that fascinating, because there are stars that are burning bright blue, and there are stars like our own that burn bright yellow, red, or kind of an orange, right? And so is it not too hard to think, is the power of this recirculation of water explodes, turns back into water, gets put back in, explodes, gets put back in, explodes, and it just keeps going in this cycle. Is it not too crazy to think that maybe the power of the suns has to do with water? Because, Jason, you probably don't know this, but water is one of the very first molecules that bind together in the universe.
They say that there's like a part of space that has all these billions of gallons of water. Have you heard that part? That there's
Tell me more.
Well, there's also a giant cloud of alcohol. I don't know. What have you heard about that too?
I would imagine, based on the voltage potential of whatever the nebula is, it will determine what is being made in that nebula. So I'm sure, yes, alcohol, sure. A whole bunch of water, sure. A whole bunch of nitrogen, sure,
Yeah.
whatever.
Yeah. And that's amazing that there's, I mean, all of those elements are out there. So what is it in seawater that's making it yellow orange?
Okay, fantastic, awesome question. Seawater has a lot of iron. It has a lot of nitrogen. It has a lot of magnesium and calcium. When you look at meteorites going through the atmosphere, and they make a color, the tails.
Right, yeah.
Sometimes you see one that's white. Sometimes you see one that's yellow. Sometimes you see one that's green. And those flame colors are telling you, as an observer, what the spectrum of agitation of the atom is. So if it's a bunch of calcium, it's going to be a certain color. If it's a bunch of iron, it's going to be a yellow color, right? If it's a bunch of calcium, it'll be a different color. So the agitation via particle oscillation as an energy generator, which is what the injector does, which a repulsor does, and what the ARC reactor does, we can create whatever photon color we want using nuclear fusion on demand.
Because you're adjusting the vibrations of through electricity, you're adjusting the vibrations, which affects what comes out of it. Right?
Correct. And if we turn on the piano, if I play a key that's way down here, it's really low sounding. That's like uranium. It's really heavy and deep. But if you play the other side, you get a super high pitch, which is like hydrogen. It's very small, tiny. Hydrogen's very tiny, right?
And speaking of stars, what if you do this? You got that one down, right?
Oh yeah, that one. Yeah, thanks to numbered notes, I can do that without even looking.
I heard you do it. I was like, wow, that's impressive.
Well, and there you go. Like inside a star, there's multiple different atoms that are exploding. And so, yeah, it's going to give off different colors. And this is what we do when we study stars. We determine like its spectroscopy of like what emission level it's giving off. Oh, that star is made of calcium, or that star is made of, whatever.
And that's because the waves of energy that you see are a particular frequency, therefore they're a particular color.
And that's what you see as an observer, because the energy is coming at you, and you get to determine it.
Now we were talking a little bit about the periodic table, and I on our Zoom call, McKane and I have all these conversations, and we always have to like cut them off and be like, let's talk about that on the podcast. So I finally get a chance to actually talk to you about everything,
And so you guys are coming along for the conversation.
Yeah, exactly. So there was a version of the periodic table that I showed you where it had those like waves, and this is the thing Terrence Howard was talking about too, right?
Yeah. Walter Russell is the guy's name who made the periodic table that looks like basically a Fibonacci spiraling out periodic table. And the thing about Walter Russell and Terrence Howard is that they are kind of like artists. They're kind of thinking outside the box. And though those ideas are really, really good and they're really, really wonderful and they do have some validity, it's not generally accepted in the academic community. And here's the thing that I've noticed through going through this experience for like 7.5 years.
Amen,
8 years.
Man.
And you can attest to this too.
Hung up on. Yeah.
Well, okay. So the first time you came up with numbered notes and you were like, I'm going to go teach the academic people and they're going to love it. And that was your first thought. Like, they're going to just eat this up like it's cotton candy, man.
They're going to receive it with open arms. Yeah.
Well, what was your experience?
I literally called, I won't say which university, but a couple of them, and they don't want to hear it. They're just like, there's another way to do it. We already know how to do it. We do it our way.
Right.
They don't want to, and even when you can show benefits, and even when you, again, I'm preaching the choir back and forth, but when you can even demonstrate that it works and it works better and it works faster and it's easier, and people, like in my case, they can learn to play music in one
session
approach. Yeah. But when you show somebody who's a professional, the reason why this is what I think about why there's a resistance to it.
Sure.
A barrier to entry with new ideas, because so many people come up with new ideas. So many of them are not really what people have been sold so much snake oil stuff that maybe we do it too. Like your first reaction is like, that can't be real. If that was real, we'd already be hearing about it in a different way.
Sure.
So how can you bring something that we already know works a different way? What was your experience with that? You must have hit some big walls too.
Very similar experience with the Quantum Kinetic Well technology with the ARC reactor using fusion on demand. Was essentially we showed people our work and they were like, no, I don't understand it. I don't really need it. It's not really helpful because I don't want to ruin my reputation and I don't want to have a big change because change is hard.
And their careers on the line, their credibility too, right? If they go off on your idea, they're putting themselves out on a limb, right?
Correct. And the thing about it is most people that you try to talk to about this stuff, they're already on a career path, which they put their chips in. I'm all in. I'm chipping in. And if you come to them and say you should fold and do something different, well, they're not going to fold because they're going to lose all your coins. Right. They're not going to start over. And so we're dealing with this dilemma where we're like, look, we've got these humongous creature things that just don't want to move. It's like trying to push a whale back into the ocean when it got beach. It's like, you should go back in the water, man, but like, I'm trying to push you and you're not going to want to go. So how do you get a whale to go back in the ocean to be better? And the only thing that we can do for you guys here at Quantum Kinetics is, teach you what we've learned, tell you what the future could be like, and tell you that it's all going to be way, way, way better going forward. But we need everyone to get involved. We need capital financing. We need people giving us big hugs and pats on the back and asking questions and being like, hey, what is this all about? Like, I want to get involved. And someone posted yesterday last night saying, I've been watching your guys' YouTube videos for 3 whole days straight, and I just want you to know that I want to dedicate my life to cold nuclear fusion. What's my first step? And to me, who's been drudging in the mud and doing push-ups in the mud and the rain, that was like an awesome message that's like, hey,
right.
Maybe we are making a difference. Maybe this is something that is going to change the world. And my goodness, I like in my mind, I would be like, the perfect world would be, we're running on clean energy transportation. We got clean energy flying machines. People have got Iron Man suits, going to go somewhere, and all these things are possible. And the ocean, the pH level rising so we don't have acidification and losing the coral reefs. Like, I'm going to tell you guys, all these things are possible with cold nuclear fusion. You just don't know about it yet. It is here. It's been proven. And now we just need to get some people behind us so we can go and build and have some fun.
That's exciting. I mean, it really is. And what kind of question do you get the most on? I haven't really read through the videos, the comments on the videos, although I understand they're doing really good.
There's some ups and downs. At first it was like negative. Yeah. And now that we're at like over 250,000 subscribers and we're growing like crazy, now the comments are actually going, hey, wait, is this it?
Yeah.
It's so, thank you. It is so cool, guys. Like, I am like deeply honored. We as a group are deeply honored. It's so cool. So keep it going. This is really your tech. It's not even my tech. It's not even our tech. It's your tech. You just don't know yet.
Well, that's great. And if people write in comments, do you respond to the comments? Or
I do my best, yes.
Yeah, that's great. I think that's exciting because I think there's a lot of people out there that they want to get involved. Is that a way to get involved? It's just
keep commenting and keep liking and keep telling your friends to subscribe and grow the channel and grow the movement. I mean, you guys, this is, I say it once, I'll say it 1,000,000 other times. Like, this is your tech. You just don't know it yet. The ARC reactor inside of you is what's powering. You are also a cold nuclear fusion reactor using that negative state pulsing resonance. Bonk, bonk, bonk. The heartbeat is, I'll give you guys a little bit of a secret since you've been here for 45 minutes, is that the pulsing action of the ARC reactor fusion on demand mimics the energy grab. It's an energy grabbing from another place to get the heart to pump. Energy grab, get the heart to pump. It's almost as if the heart is actually going just for a split second, going back in time and then going forward, back in time and going forward. It's almost like a clutch.
Huh.
And so that's how it gets its extra energy. It's clutching. And that's all I'm going to say about that, because I don't want to go too far.
I know. I was just thinking, like, isn't that just muscle? Isn't that just like muscle, like nerve fire, muscle contracts, let go, contract, let go, like, you know?
Yeah, but if you have a battery sitting on the table and how do you get the battery to pump? It has all this voltage, right? It's potential. It's 12 volts, but it's not doing anything. How do you get it? There is a mechanism to make a potential voltage get extra energy. There is a way to do it. We talked about it in the beginning of the episode a little bit first.
That reaching across this is so fascinating to me, this idea of the veil, you know,
yes.
the
0 point energy.
0 point energy.
Yes.
That, like, again, out in space, that's happening, right? Where there's a flicker of, what did you call it?
The quantum vacuum flux is flickering light all the time.
Okay, even though there's nothing out there, nothing out there, but is it, okay, what's going on out there? Why is there little sparks of energy happening out there?
So, there's a guy by the name of Paul Dirac. Paul Dirac got a Nobel Prize around 1943. He did a mathematical equation way back in 1933, and he discovered that if you take the square root of 9, it's 3 and -3. And he thought that was very peculiar.
Oh, right, because -3 times -3 is 9, and 3 times 3 is 9.
And so there was this thing that he saw, because he was a theoretical physicist who was doing math too, and he thought to himself, well, wait a minute, even when you do x squared, you get a parabola going up, or you get a parabola going down, depending on what, negative or positive. And he thought that maybe, just maybe, there is an electron, and there's this weird thing called a positron, which is a positively charged electron in the Dirac sea, which is basically the quantum vacuum flux, where an electron pops into existence automatically, because the square root of 9 is 3 and -3, you get a negative mass. He got a Nobel Prize for it.
Is this supersymmetry?
The academic community would not agree with that being supersymmetry. They think supersymmetry is like something slightly different. They don't attribute it to the antimatter. They attribute it to something like, I think it's dark energy, which, by the way, dark energy is a bunch of bullhunky, to put it nicely.
A bunch of dark mass.
As Sabine would call it, gobbledygook. But yeah, so dark energy, garbage. Antimatter, matter, good. Positive light, good. Negative light, good. It's that simple. That's supersymmetry. Keep it simple. Kiss.
Now, we were talking about in the beginning the periodic table and the electromagnetic spectrum. Yeah. So, switching over to electromagnetic spectrum.
Perfect.
My understanding of the electromagnetic spectrum is that it's a what's the word I'm thinking of? Where you have a spectrum.
Yes.
Of course, it's built into the name. It's based on the name.
Well, then you have to ask yourself, what does it mean, the word? Like, we were talking a little bit at lunch about, like, language.
Right.
When you say the word spectrum, well, are you talking about someone's behavior as a spectrum? Or are you talking about light as a spectrum?
Well, okay, so what I'm thinking about, when I say that, I mean, like, just like the piano. So we have frequencies getting more dense per unit of time, right? So
yeah, so the wavelength's getting tighter and tighter.
Right. So when it's super tight, is that like X-rays?
Yeah.
And then when it gets less tight, we're talking about like visible light.
Yes.
And then what is ultraviolet? What goes?
So it would be, now you're into infrared.
Okay.
That would be like infrared.
Okay, where they're getting really stretched out.
We should talk about the degrees of freedom of electromagnetic spectrum.
This
is very good.
Yeah.
So go ahead and hit the X-ray. Okay, that's electrons shooting off. The X-ray comes in, it's very tight and small, and it shoots off the electron as an ionization. That's a degree of freedom. Okay, now go down to the visible light. Okay, so that would be like a wave that's longer and it hits an atom, and then it doesn't knock the electron off. It just moves the electron into a different shell orbit and then back, and that re-radiates the same light so that you see the reflection of the wood, the metal, the camera. That would be another degree of freedom, which is visible light. It interacts with the matter different. Then infrared, that would be the electron or the electromagnetic radiation that's longer, hitting the atom and causing it to do what? Wobble or agitate or like wobble back and forth, which causes heat.
Right. That's what heat is, right?
Yeah.
Excited atoms.
It's a vibration like this. The whole thing is like, whoa, my core is vibrating now, bro. This is crazy, right? It's just jittering.
And then we have down here the Barry White of all electromagnetic spectrum.
Radio. That would be like the long wave radio,
right?
Which just makes the electron in the shell go, wow, wow, wow.
And
it doesn't really do anything. It just wobbles it.
And super, super long is gravity waves, right?
Well, super, super long would be like audio waves.
Oh.
Like the sounds. Those are long wave, really long waves.
Okay, so
compression.
Just getting a little bit, taking a little side tangent on the side tangent.
Yeah. That
thing where they test gravitational waves, LISA, right? Or Largo or whatever.
Largo, LISA.
Yeah. LISA's the one in space.
Acronyms.
Yeah. I know it's in Eastern Washington, and it's like this weird like L-shaped thing where they're detecting if an atom, by using lasers at different angles, if it's wiggling.
It's very similar to the way that the Michelson-Morley experiments kind of worked, actually.
Huh, what is that? Like
the Michelson-Morley experiment is just an interferometer that detects the ether drift via a light spectrum diffraction. If you move it, you'll see a diffraction moving, which would be the ether drift. Very similar to what you're talking about, where they have these things that are at 90-degree angles of each other, and they're detecting one signal versus another one, and they can determine the gravitational flux. Right. Now, here's the thing I remembered about Einstein being wrong about. He said that gravity is a constant. Big revelation, gravity is not a constant. It actually, it fluctuates like my microphone. It actually moves and changes and undulates. It's a scalar wave. It's changing all the time, like a barometer. Gravity is not a constant. It's changing all the time. And I'll tell you why. Is because we, on planet Earth, are rotating around the sun. The sun is also rotating around a galaxy. The Milky Way galaxy is rotating around the big galactic center. So we are going through multiple different gravitational flux fields all the time, and they're changing based on where Jupiter is, or where Mars is, or where our moon is.
Right, yeah.
So you can see that it's a multi-dynamic thing changing all the time.
Yeah.
It's not constant. So
well, even, to kind of prove the point, look at tides, right? I mean, a tide rolls in and rolls out because the moon is spinning around.
And I will go as far as to say, based on what I know about cold nuclear fusion, is that if we lose the moon, we are all gone. There's a very symbiotic relationship to the moon, which actually in myth, she was actually the goddess of fertility and love and all this stuff. She was a creator. So even the mythology of the moon indicates that she's important to the life on Earth. So we're at 50 minutes or 53 minutes. Is there anything else you want to talk about before we close out? Because we got to keep them short for our producer.
Okay, yeah, short and sweet. But there is one other thing I wanted to ask you about.
Sure.
You talked about making the suit.
Oh, yes.
Can we see a chunk of it? Or,
yeah, so just to give...
Well, how about the helmet? I mean, come on, let's see the good stuff.
Then it's right there. I'm working on it. And we're working on it. And so... Just real quick, we talked a little bit about this in the other episode about the X-ray protection. Is that if you coat your suit with a silver plate electroplating, you can actually deflect and absorb X-ray emissions. And so, because of this is cold nuclear fusion and it does emit some X-rays, we are basically getting ready to do that.
It's so cool.
It's tough when you have a shoestring budget to really get this stuff done because, we're doing all these other things, like we're getting patents and trademarks and keeping the business going and doing YouTube and just a half dozen other things. But the point is, ladies and gentlemen, we really need you guys to like help out, get involved, be a part of this movement, because we can't do it alone, and we certainly don't want to do it alone. We're really excited to change the world for the better and give an opportunity for, you know, your kids and your kids' kids to have a green planet going forward, because right now at this current trajectory, you know, we only have so much time, and I'm not going to say specifics, but it's pretty bleak. It's kind of something that people don't talk about. But anyway, let's leave it on a good note that, yes, we are working on the Iron Man suit. It's all in the works right now. We're working on miniaturizing the quantum kinetic injectors for the repulsors in the hands. And next episode is going to be episode 3, season 2. We're going to be having Brighton back on the show. And we're going to be talking a little bit more about the gravity and the catastrophe theory. Kind of a more of a Russian concept that's been forgotten, and how that's linked into the Paul Dirac matter, antimatter, and nuclear fusion agitation. So,
well, I wanted to say one last thing.
Sure,
in closing, is just to invite everybody out there to send in your comments. Tell us what you'd like to see. Tell us what you're interested in. Tell us what your thoughts are on the technology and the presentation so far. Mm-hmm. And then we can respond to that, you know, create some cool images, show some cool stuff, talk some more about some interesting topic.
Yeah, absolutely. I mean, this is like very much the Sesame Street. So you guys tell us what you want, and we will give you the best we can of what we can without sharing too much, without giving away trade secrets. But like, we have a lot of knowledge. Like, I've been teaching Jason about the technology. He's learning rapidly fast. Matter of fact, he's learning so fast, I'm actually kind of impressed. You know, even Randall, he's learning super quick. Brighton, he's just smart as a tack, and he's sharp as a tack. Like, he gets it right away. And you guys are starting to learn too. And so when we see you guys writing comments like that, it just really tickles us, gets us excited. It agitates our antimatter, you know, our engine. So thank you so very much. And keep tuning in and keep subscribing, and we'll see you guys on the next show. We'll be showing in about 2 weeks here. So
sounds good.
Thank you so much for coming on, Jason. As always, you're a superstar.
Fun. Thank you.
So, all right, ladies and gentlemen, again, thanks for tuning in, and we will see you guys next time.
See you next time.